PI controller, performance and modeling for the voltage system between 0 and 10 volts. It's outlining, go through background and theory, go over some previous work, talk about the proportional integral modeling and the performance, and draw a conclusion. Here's our block diagram. The computer goes to the variable frequency drive, which steers the motor, which steers the generator, which produces power, like the lights, and then it gets back to the computers with the data. Here's our SSOC stuff. Between 0 and 67% input gives us 0 to 10 volts SSOC curve.
That's interesting. Everybody say that's interesting. Yeah.
No.
Well, our operating range is actually between about 12% to 67%. Below 12%, there's a lot of oscillation, there's a lot of noise, and produces quite an interesting set of data. So it's hard to use that data. So we use our operating range between about 12% to 67% or so to get the 0 to 10 volts. Here's our step response results for the gain, the K between the experimental models. You can see how there's a couple of outliers between the experiments and what we found modeling, and this has happened a lot with our voltage system. Is that what we find in the experiments and what we find in the modeling are almost two completely different things throughout our different experiments. You'll see that a lot here. So our average time constants, as our ranges go up, the time constant seems to increase a little bit, not very much, but a little bit. And again, we have a couple almost outliers of the tau. Frequency response is block diagram, how that works, the forcing function. Here's an example of one of the frequency response curves. Is you can find tau and all that stuff. The equation for Bode. And here's our Bode plots. And this is actually an interesting set. It has the model and what we found from our phase angle from our frequency response. And this is towards the lower section, about 20%. The baseline is 32%. And if you'll notice the blue line, there's actually almost two different curves that you can model this to. That's one thing that we found is that in the center, there's a little bit of a plateau, and the curve for the model you can actually fit to the right-hand side of that plateau or the left-hand side, depending on what you want. So even in our modeling, we get two separate answers from what we found experimentally. Here's the results from the frequency responses. For the most part, our FUs and amplitude ratios and KCUs were about the same, except for the KCU for the lower section between the 20 to 42% was a lot higher than the other two ranges that we found, and everything else seems to coincide fairly well. Here's the gain for the lower, middle, and high between the observed and modeling. I think this is for frequency response. They're pretty much the same. They're off by a little bit. Not too much of a difference between the modeling and the observed. The same, the first order time constants are very similar between what we observed experimentally and what we observed from the models. And again, same with the dead time, which is practically the same between what we observed and the modeling itself. Here's the relay feedback that Brian S. did for us, and he produced this plot for us, and his results were right here, the delta C's, delta M's, the amplitude ratios, and everything else. You can see it here. The proportional only control model, these are the functions. Here's the root locus plot, just an example of how you find the different decays at the different angles. And for our proportional only control model, you see that for the middle and high section, all the KC values were very similar, very close to one another, and the outliers are actually on the lower end. We have a very high KCU value, all the way down to even the critically damp is quite a bit greater than the other two sections. And you can see at what phase and what angle you find this from the root locus plots. Here's a graphical example. It's just the results from the previous page. You can see how the lower section is actually a lot different than the middle and the higher sections that we did. This is actually the example of the gain at 20%, 15% for the lower section. You'll notice, especially on the top two graphs, there's at a higher gain, there's a lot of oscillation. And as you move down in the gain, you actually lose the oscillation and you pick up noise, which is just on the bottom two graphs right there. And on the bottom two graphs, you get closer to a small gain, you actually get more critically damped. Is the functions for the proportional integral controller. Here's all of our values that we found. For that, yeah, it's on the very last line.
So notice that right in the middle of the bottom, 0.03 for a Tau-Ci, it's their smallest Tau-Ci. And notice how the root locus says that KCU is the smallest of any of them. And this one over here, remember what the KCU was for proportional only was 43 years, wasn't it?
The KCU, it was actually 58. For this, we used, what I did was take a tau I of the 3.33 times T0 to find a tau I, and actually the graphs performed, or the output performed a lot better than what I found with the proportional only. And it changed our value, my values for KCU, critically damped, K values and all the way down, but it didn't change it all that much, and it actually didn't help as much, but it helped a little bit.
Notice bottom line there, for Tau-Ci large, by large I mean about 3 times T0. In fact, that one in the very bottom right is 4 times the dead time. No, it's 5 times the dead time. But notice that all of those except for the 0.03. Ultimate KCU is ballpark the same thing it was for P-only control.
Right.
So if you use that formula of 3.33 times Tau-Ci, you're going to get about the same ultimate gain. If you use something smaller like that 0.03, is that 1/4 of the other thing?
Yeah, I believe so.
Ballpark. Then your KCU drops off.
Right.
In fact, all of those KCs drop off. KCU, quarter, 10, 500. Smaller Tau-Ci means the system is more unstable, so you're going to have to drop KCU, KC.
But here are all our KC values. Low, middle, and high. Relay. Here is.
Everybody say, hey, that's nice.
These are graphs between the left side is the high section, the right side is the middle section, and that's I believe it's with the tau I of the very, very small. You get a really nice, especially on the 10th decay.